Okay, my dear students, in the last class we discussed about the one-to-one and onto maps rank nullity theorem, and now in this class we discuss about some important results and some more examples on one-to-one and onto linear transformations. Okay, let's start with an example. We have to check let T from P2R to P3. This is a polynomials to P2 to P3 over the field of real number be a linear transformation, and defined by T of fx is the form of a 2 times of a derivative of fx plus integration of 0 to x 3 ft dt, where Pn is a set of a polynomials of a degree at most n with the coefficient from the R. So we have to just check the basis of P2 R basis. We just take a basis. So basis of P2 is nothing but is equal to 1 x square, and you have a basis of, we have a P3, we have a 1 x square, and then we have a x cube. So first we calculate the T from the on the basis of this. This fx is the element of a this fx we have to is the element of a we have a P2 x or we can say the P2 over the field of R. Okay, so we just this basis. So we calculate first is a f of T of 1 fx is equal to 1 x square. So we have a T of 1. T of 1 is nothing but is equal to 2 of f derivative of this, f is equal to 1. So derivative of 1 is equal to we have a 0 plus you have just said that integration 0 to x, you have a ft and dt. So this means we have to write three times. So 3 times 1 into dt, that is equal to, this is 0, this is equal to 3x. Now we have to calculate similar fashion T of x is equal to 2 into 1, derivative of x is equal to 1, integration 0 to x 3x and dx. This is equal to 2 plus you have a 3 by 2, and then you have a clearly the x square, and then we have a T of x square. This is nothing but is equal to 2 into we have a derivative of x square 2x plus integration 0 to x 3 x square, then you have a d of t square, sorry, this is t, this is t or dt. So t square dt, and this is nothing but is equal to you have a 4x plus you have to just say that 4x, then you have a 3 by 3, you have a x key power, we have to just say that x key power 3. So this means this is can be written as a 4x plus you have a x cube. So we have to calculate all this T1, T2, T3 up to this. So these are the form of the Tx, and then we have to, this is clearly Tx square is equal to we have a 4x plus x cube. So thus we can say that RT is nothing but is equal to span of this, and this is clearly this set is a linearly independent. So RT is equal to this means basis, in that basis of RT is equal to, you can say that in the form of this. So we can just say that this is a linearly independent set. So we can say that there is an element is 3. So we can say that dimension of RT is equal to 3. And now by the dimension rank nullity theorem, you know that dimension of a V is the same as a dimension of a RT plus dimension of kernel of a T. Dimension of a V is you have a 3, and dimension of RT is equal to 3. Then you have a plus dimension of a, you have a kernel of a T. This implies that we can say that dimension of kernel of a T is equal to 0. This implies that we can say that kernel of a T is nothing but is equal to you have a 0 subspace into this one. Okay, so this means RT is equal to dimension, but this is RT is a dimension of a RT, you have a 3, and then you just say that the T is mapped from, you have a P2 to P3. So, this is a proper subset of this, is not complete, is though this set is not an onto. The rank nullity theorem, we can say that kernel of a T is equal to 0, and then T is clearly is a 1 to 1, but is not an onto, because this dimension of a RT is equal to, you have a proper subset of a this thing. Okay, now we try to prove this result. We saying that there is a very important condition in this. We have to this dimension of a V is the same as the dimension of a W. So, V and W be two vector spaces. T from V to W be linear map with dimension of a V and dimension W are the same, means we can say that both the vector spaces have the same dimension. Then if T is 1 1, then T is onto and RT is equal to whole W. There means we can say that all these three conditions are equivalent. So, we start from T is 1 1. Now, we have three cases. If T is 1 1, then we have to start T is 1 1 means we have a kernel of a T is equal to. So, we start first is a T is 1 1, if and only if you know that the result T is 1 1, if and only if the kernel of a T is equal to 0. So, we have to show that clearly T is onto. So, we just said that if T is 1 1 kernel T means dimension of a kernel of a T is equal to, you have a 0. Then by the rank nullity theorem, we can say that dimension of a V is the same as a dimension of you have a range of T plus dimension of you have a kernel of a T, and dimension of a V is the same as a dimension of a W. So, we can say that dimension of a W. So, this means we can say that this implies that dimension of W is the same as a dimension of range of a T plus 0, and this implies that we can say that dimension of range of a T is the same as a dimension of a W. So, if dimension of a RT is the same as a dimension of a W, then we can say that this both the dimensions are the same. This implies we can say that T is onto or RT is the same as a W. We can say that both the dimension is the same. This means RT is the same as a W. So, this we can say that. So, this means we can say that this RT is the subspace of a W, and hence T is a onto. Therefore, RT is equal to W. We can just say that. Okay, so now we have to just this is this should be, we can say that dimension of a V. This is minus m. Okay, RT is equal to dimension of a V is equal to dimension of a W minus dimension of a this is equal to, you have this is okay, this is no. So, we this is a mistake here. We say that dimension of a RT is equal to dimension of a this is equal to this is in the bracket is the since dimension of a kernel of T is equal to 0, this thing. Okay, so one case if we have to show that T is 1 1, then by the we can say that this T is a onto. Now, we have a T is onto if T from we have a V to W. So, for each W belongs to W, there exists some V belongs to V such that T of V is equal to W by the definition of a since we have a T is onto. So, if T is onto, then we can say right into this thing, and this means we can say that so if this T of V is equal to this, so T is onto means we also can say that rank of a T is equal to same as a W, and then we can say that dimension of RT is the same as a dimension of a W, and again by the rank nullity theorem we can say that dimension of a V can be written as a dimension of a RT plus dimension of a kernel of T, and dimension of a V and W are the same. So, this can be written as a dimension of a W is equal to, this is also RT is equal to dimension of a W because T is onto. So, this we can say that dimension of kernel of a T, kernel of a T, and this implies that we can say that dimension of kernel of a T is equal to 0. This implies that we can say that kernel of a T is equal to, you have a 0 subspace, and by the theorem we can say that this implies that T is 1 to 1. So, this completes the second case. We have a R T is equal to 0, then we can just say that by this. So, this is imply kernel of this, we can say that clearly T is a 1 to 1. Now, in the case third, we have a R T is equal to, we have a W, then it is obvious if R T is equal to this, then T is onto, and because dimension we have to again this is onto. So, this means general this R T is equal to dimension of a V is the same as the dimension of a W. So, this means again V and W equal dimensional vector spaces. So, we can say that this is again this thing. So, we can say that again T is a, you have a 1 to 1. So, that means we have to, on all the cases we have to prove that if T is 1 1. So, if that is a very important result, we can say that dimension of a V is the same as a, if dimension of a V and W are the same, and if T is 1 1, then T is also onto. If T is onto, then we can say that T is also 1 1. So, that means we can simply, if we have any problems, we can easily calculate is a T is 1 1 and onto by using this theorem as a application. This theorem is a very important using into this form. So, this way we can say that this is a very important part. Let us try by the one more theorem. This is say that we have a V1, V2, Vn basis for V and T V a Vn to 1 and on to linear transformation, then the set is a basis for W. So, that means we have giving us two conditions. We have a T from V to W be a be 1 to 1 and on to linear transformation, and this B is a basis. So, this V1, V2 is a basis, means we have two things is there. So, we have to just say that this is this V1, W is basis, means is a linearly independent, and span of this all this is equal to V. Now, we have to show that this set is a basis for W. So, if we try to show that this is a basis for W, means we have to show that this set is a linearly independent and also generated by the set. So, we have to this is a basis for W. Now, we have this is a show that this is a basis for W. Now, because this is the basis of a W, means we have to show that this is equal to two things is linearly independent, and span of this set is equal to, you have a W. Okay, so we just using this. So, we let us try. We have to write for first we try to linearly independentness. So, we just write a linear combination of this is equal to some 0 vector, and now T is, you have a giving is a T is 1 1 and on 2 map. So, this means for a W belongs to the W, there exists some V belongs to the V such that T of V is equal to, you have a W. So, T of Vi is equal to, you have a Wi. There exists any for Wi belongs to the W, then Vi belongs to the V such that T of Vi is equal to, you have a Wi. So, this means we can just write into this form. By using this, we can just say that first we using the linearity condition, since T is a linear, into this form, and now if this can be written into this T is a linear into this form. So, we can say that this T of this thing is equal to 0, and hence this V1, V2, Vn belongs to the kernel of T. If this is belongs to the kernel of a T, but you know that this so this kernel of a T means we have to just show that since T is a 1 1. So, this kernel of T is equal to, you have a clearly is equal to 0. So, this means we can say that if V1, V2 this is kernel of a T. So, by the definition of a kernel, this vector is but T is 1 1. So, this kernel of a T is equal to 0. So, this implies that we can say that this alpha 1 V1 plus alpha 2 V2 plus so on, we have a alpha and Vn also 0, and we have a set, if you remember, V1, V2, Vn is a basis for V. If a basis of V, this means this is a linearly independent, and so this means these vectors are V1, V2, Vn is a linearly independent. So this implies that we can say the alpha 1 is equal to alpha 2 and so on is equal to alpha n is equal to 0. So each of scalars are is equal to 0. So this means we have to show that the linear combination of this is equal to 0 vector. Then this implies that you have a this alpha 1, alpha 2, alpha n are 0. So this means we can say scalars are 0 means this set of vectors t of v1, t of v2, t of vn is are linearly independent. So this means we can say that this is a clearly first part is completed. Now again this is a basis for a vector space V. If a basis of vector space V, then we can say that then span of you have a V1, V2 up to Vn is equal to V, and we have a result is there span of if we have a span of V1, V2 up to Vn is equal to V, then we can say that then RT is nothing but is equal to if you have a. So then by the result this RT is equal to span of T of V1 up to T of V, and so this means by this result we can say that this can be written as a span of T of V1 up to T of Vn is equal to range of a T. Okay, so this means but range of a T is what? This is range of a T is equal to W. Why? Because T is onto. So this means we can say that by this result this can be span of a this is equal to you have a W. So what we show that? We show that this T of V1, V2, Vn is linearly independent, and T of span of a T of V1, T of V2 up to 2Vn is equal to W. So that is clearly this satisfies both the condition of the basis. So if we have a V1, V2, Vn is a basis and the linear transformation is a 1, 1 and on to linear transformation, then clearly we say that that T of V1, T of V2, T of Vn is a basis for a W. So this means this clearly we can share this, say that this is also is a basis for a W. Okay, so now this complete the proof of this result. So whenever we have a 1, 1 and on to mapping there, and V1, V2 is the basis of a vector space V, then clearly we say that the image of T of V1, T of V2 up to T of Vn are also is a basis of a vector space of another vector space of a W. Okay, so now we start. Let's try to check. This is the thing. Now you see we have a clearly given you have a both the vector spaces is the dimension of V and W are the same dimension vector spaces. So we check whether it is a 1, 1 onto or not or bijective or not. So that means we can just because of the theorem we can say that if T is if the dimension of we have a result clearly just now we have to prove that dimension of a V is the same as the dimension of a W. If T from V to W is a linear map, then if we have to just say that if T is 1 to 1, if and only if T is on to. So if T is 1 to 1 and T is on to, by this we can just try to prove this if this is T is 1 1 because is also is on to because of this map from R to R is there. Okay, so we try to this first take a kernel. So we have a kernel of this is the form of this thing, and kernel of this is clearly T of x y z is equal to we have a 0. So T of x y is defined to this form. So this means this is equal to 0. Then this is clearly is saying that x plus y plus z is equal to you have a 0. And if x plus y plus z is equal to 0, z can be written as a minus x into minus y. Then we can say that kernel of a T is nothing but is equal to we have to is the form of this you have a x y minus x minus y such that x and y are the element of a R, and this is nothing but is equal to we can say that this is a span of the this form is equal to 1 0 minus 1, and then you have a 0 1 minus 1, and this is the kernel of a we can say that this x plus y such that x and y are the element of R. So this means we can say that kernel of a T is nothing but is equal to you have a span of 1 0 minus 1 0 1 minus 1. So this means clearly we have to just say that kernel of this is not equal to 0. So, kernel of we can just say that kernel of T is clearly not equal to 0 subspace. So, this means clearly this is T is not an 1 1. So, this means clearly we can say that into this form. So, this is clearly this T vector is linear independent, dimension is equal to 2, hence T is not a 1 1. So, because dimension of kernel of a T is not a 0 subspace, and then clearly T is not onto not a 1 1, but we try to find that it is onto or not. Because dimension of a, you just say by the dimension theorem we check is onto or not. If you check by the rank nullity theorem, we say that dimension of R3 is the same as the dimension of kernel of a T plus dimension of range of a T, and then this is equal to 3, and dimension of a kernel of a T you have a 2 plus dimension of you have a range of a T, and this is clearly giving you a dimension of a range of a T is equal to 1, and this is because, but the T is mapped from, you know that T is from R3 to R3. So, this means clearly RT is not equal to the whole of the R3. So, this means is clearly T is also not is onto. So, this is RT is nothing but is a proper subset of a R3. There is a proper subset of this. If it is a proper subset of this set, then clearly we can say that this map is clearly is because by the previous result also we can say that, because both the dimension are the same, if and only if condition are there, if T is 1 1 then R is onto. So, T is not onto, but we have to try to check this. So, this means we can say that is not. So, this means T is not onto. So, hence T is not a bijective. Let us try another problem. We have again we take a same maps, and the basis vectors are there for R3, and this is basis vector for this R3 respectively. We have to find the kernel, range, dimension of this, is T is bijective or not. That is all the profit. So, this is clearly defined in the form of this. You have a T of, you have a 0 1 1 is the form of a 2 0 0 form. T of 1 0 1 is the form of a 0 2 0 form. T of you have a 1 1 0 is the form of a, you have a 0 0 2. So, these are the basis vector. So, this any vector we have to choose any arbitrary vector we can choose. We directly can solve this. We can just write any vectors x1 x1 x2 x3 is the element of a R3. Then this can be written as a finite linear combination of the vectors of this basis, and then we have to apply this. So, this means we can say that x1 x2 x3 can be written as a, we have a some alpha times of a 0 1 1 plus some alpha 1, we have a alpha 2 times 1 0 1 plus alpha 3 times you have a 1 1 0. We find the value for alpha and beta in terms of this, and then we operate the T on the both side, and then we can using this and then try to solve this. Okay, so let V is equal to, we have to take a V1 V2 V2 is equal to this, and alpha 1 alpha 2 alpha 3 are the scalars of R. Then V can be written as a linear combination of these things. So, this is clearly can write in the form of a this is 0. So, you have a alpha 2 plus alpha 3. Now, you have a alpha 1 plus alpha 3. Now, you have a alpha 1 plus alpha 2. So, this means we can say that you have a alpha 2 plus alpha 3 is equal to V1, and you have a alpha 1 plus alpha 3 is equal to you have V2, and now alpha 1 plus alpha 2 is equal to you have a V3. One of them you have to, now we have to solve this system of equations. Okay, so thus we have to write in this form. So, this means we have to try to solve this form. Anyway, you have to just try to solve this. We have a like this alpha 1 alpha 2. So, just I write alpha 1 plus alpha 2 is equal to V3. If we have a subtracting these two, we just write above. It's not a problem. We just write in the form of a alpha 2 plus alpha 1 is equal to you have a V3. If we take a subtracting these two, this is cancel out. So, you have a alpha 1 minus alpha 3 is equal to V3 minus V3 minus you have a V1, and you have a alpha 1 plus alpha 3 is equal to you have a V2, again cancel out. So, you have a alpha 1 is equal to 1 by 2. is equal to, you have a minus V1 plus V2 plus V3, and you have a alpha 1 is there, then you can calculate all others values also. So, if you have to this alpha 2 is equal to, you have a V3 minus alpha 1 by 2 minus V1 plus V2 plus V3, and this is nothing but is equal to, you can just check, is equal to 2 times of a this. So, this is minus is a plus. So, you have a 1 by 2 V1 minus V2, and then you have a plus ka V3, and similarly you have to calculate the value for alpha 3. So, alpha 3 should be is equal to 1 by 2, you have a V1 plus V2 minus V3. So, we have to getting all this values. So, this is in this form. So, we have a all alpha 1, alpha 2, alpha 3 is there, and either we have to substitute in there or we can separately calculate. So, T of V is nothing but is equal to this form. So, we have to equating and substituting the value for this. So, T of V is nothing but is equal to, you can just say that T of V is the form of this, alpha 1 is equal to this, so by 2. So, we have to is equal to this, alpha 2 is this, and so on. So, we have to substitute the value for here. So, we can T of V is equal to this form. So, this we have to first we calculate the general form of a T of V. So, now we check is this is a 1 1 on 1 1 and on 2. So, we check the kernel of this kernel of a T of this. So, kernel of a T is nothing but V belongs to the V such that T of V is equal to 0. So, this implies that we have a this implies that you have a, this whole thing is equal to, so V2 plus V3 minus V1, V1 plus V3 minus V, sorry, this is 2, sorry, this is 2. So, this is 2, then you have a V1 plus V2 minus V3, and this is equal to, you have a 0 0 0. So, this implies that you have a V1 this is, we have to just say that we have to write as a V2 plus V3 minus V1 is equal to 0. Then you have a this is equal to minus ka V2 plus V3 plus ka V1 is equal to 0, and then if you adding this is these two giving you have a V3 is equal to 0, and if V3 is equal to 0, then we have to again substitute V3 is equal to 0, V1 minus V2, V1 plus V2. So, V1 is equal to 0. So, this means if simplify that we have to getting all the vectors V1 is equal to V2 is equal to V3 is equal to. So, this is V3 is equal to 0. Now, substituting V3 is equal to 0 here. So, you have to take V2 minus V1 is equal to 0, and this is equal to we can just say that V1 plus you have a V2 plus V1 is equal to 0. So, this is cancel out. So, V2 is equal to 0, and substituting here you have a V1 is equal to 0. So, this is all the scalars this vectors are equal to 0. So, we can say that kernel of a T is equal to 0 subspace. This implies that T is 1 to 1. So, this means we simplify this, this is equal to 0, this is equal to, you have a 2, okay. This is equal to 2. So, this means this is equal to 0, then we have a gives that is equal to, this is 2. So, V1, V2, V3 is equal to 0. So, we just say that this all the V1, V2, V3 is equal to 0. This is success, T is a kernel is 0, T is 1 1. So, dimension of kernel is equal to T 0, and then by using the dimension theorem we can say that, and by because both the dimensions are the same, the T is also onto. Dimension of a W is dimension V is the same. So, we can say that T is also onto, then if is onto, then RT is equal to, you have a W, and W is equal to, you have a R3, and dimension of a RT is equal to, you have a 3. So, this means clearly T is 1 1 and onto, and the dimension of a kernel of a T is equal to 0, and dimension of a ring of a T is equal to 3. This is also verified by the theorem, because is the rank nullity theorem can also verify here. Now, you know that the rank nullity theorem says the dimension of a V, this is dimension of a V is nothing but is equal to dimension of a R3 is the same as the dimension of a, you have a range of a T plus dimension of a, you have a kernel of a T, and this is equal to 3, and rank is equal to, you have dimension 3 plus 0, and this is clearly is a also verified here. Okay, so now I just tried one more example. Is this we try to show that this is neither 1 1 nor onto. So there is a two way. We just say that we have a T of E1 is equal to this form, T of E2 defined into this form. They are E1, E2, E3 are the standard basis, and now clearly you can say this is not the both not the same dimension. V and W are the different dimensions are there. So first we try to find a general formula for this. So for this span of this is equal to R3. Clearly span of E1, E2, E3, E1, E2, E3 is equal to R3. So then clearly T is you have a RT is equal to span of a T of E1, T of E2, and then T of E1 is equal to this span of this. Now you can check clearly this. If you take a sum of these two vectors, you have to just take E1 minus E2 is equal to this third vector. So E1 plus E2 plus E3 can be written as a you have a E1 minus E2 plus twice E2 plus E3. So that means these three vectors are clearly is a linearly dependent. If these three vectors are clearly linearly dependent, means you can just say that is linearly dependent, means then one can is the exclude. So this vector is a linear combination of these two vectors. So that means we can say that so RT is nothing but is equal to span of these two vectors E1 minus E2, and these two vectors are clearly linearly independent. If these two vectors are clearly linearly independent, means we have a dimension of RT is equal to we have a 2, and dimension of RT is clearly the subset of a R3. So this means clearly we can say that this T is not an onto. So this dimension of RT is equal to 2. So we can say that clearly RT is a proper subset of a R3. You can just V3 or you can just start R3. Hence T is not an onto. Okay, so now clearly first we show that T is not onto. Now we try to find that T is 1 1 or not. So we just take a T of x1, x2, x3 is equal to T is 1 1, check kernel of a T. Kernel consists of those vectors in R. T of x1, x2, x3 is equal to 0. So T of this can be written as a finite linear combination of the elements of the basis E1, E2, E3 is equal to 0. T is a linear, then means this can be written in the form of x1 T of E1 plus x2 T of E2 plus x3 T of E3 is equal to 0. And if this is equal to 0, means we have to substitute the value for E1 T of E1 T of E2 E3, and then we have to just simplify this. You can just say that T of E1 is equal to you have a T of E1 is equal to you have a E1 minus E2, T of E2 is equal to you have a twice E2 plus E3, T of E3 is equal to you have a E1 plus E2 plus E3. So if we substituting here, so you have a x1, you have a E1 minus E2 plus x2, you have a we have a twice of E2 plus E3 plus x3, you have a E1 plus E2 plus E3. So we have to just write this, and then here is a no E1 involving. So this is means x1, and you have x1 plus x3, and now E2 is equal to you have a E2 is equal to you have a clearly this is E2 is equal to you have a, so this is x3, so this is x1, and then this is minus x1 plus twice x2 and plus x3, and then you have a x2 plus x3, this is should be minus. So this is equal to 0, and this is equal to 0 means x1 plus x3 is equal to 0, x2 plus x3 is equal to 0. So this means we can say that x1 is equal to x3, x2 is equal to, so we have a x1 is equal to minus ka x3, x2 is equal to you have a minus ka x3, and then substituting here x1 is equal to minus x3 is x3 plus ka twice, x2 is equal to you have a minus ka x3, so this is equal to minus ka twice x3 or plus x3. So this means this implies that you have a x3 is equal to you have a so this means we can just say that into this form. So this is x1, x2, x3 is equal to all of them is clearly is in this form. So x1 is equal to x2 is equal to minus ka x3. Therefore kernel of a T into this form. So span of this is equal to 1 to 1. So hence T is not a 1-1 mapping. So, this means clearly we can say that T is not a 1-1. So, this by this we can say that clearly map defined into this form T is neither 1-1 nor onto, because and T from R2 to you have a R3 and dimension of RT is equal to clearly you have a 2, and then we have a dimension of this is equal to you have a clearly is a 1. So, this means we can say that this is clearly is not a neither 1-1 nor onto is there. Okay, so now just last just a problem this we have a one more problem to discuss in this section. Let dimension of a V is equal to n and dimension of a W is equal to m, and T from V to V be linear transformation. If n is less than m, then T is not surjective, that means we can say that not onto. If T is onto, then this is clearly n should be greater than or equal to m is there. Okay, first we prove to A. We have a if n is less than is strictly less than m, so n is strictly less than m, and you have a n is equal to dimension of a V and m is equal to dimension of a W. So, n is equal to you have a dimension of a V, m is equal to you have a dimension of a W, and you have a n is less than m means by the rank dimension of a rank, the dimension of a RT should be less than equal to V. So, this means dimension of RT always less than equal to V. So, n is strictly less than m means this dimension should be less than V. So, this means we can say that RT is a subspace of a W. So, the dimension less than W, that is RT is clearly not equal to W. So, if RT is not equal to W means T is not a surjective. That means clearly RT is not equal to all. This RT is a proper subset of a W. If RT is a proper subset of a W, then we can say that this T is our linear transformation is not a onto. So, not onto or not a surjective. Now, we have to another, if T is a surjective, T is onto, and then RT is equal to W. So, if T is onto means dimension of RT is the same as the dimension of a W is a m, and again dimension of RT and then kernel of this is equal to dimension of by Rank-Null dimension theorem. Dimension of a kernel of a T plus dimension of RT is equal to V. So, and these are the same. So, we have a this dimension is a m. So, m is equal to this dimension of a RT dimension of kernel plus m is equal to n. So, this means clearly since dimension of a kernel of a T is always greater than or equal to 0. So, we have a n should be always greater than or equal to 0. So, this means n should be always greater than or equal to m is there. So, this means always is satisfied into this form. So, this clearly we can say that clearly the value of m is always into this form. So, this completes the proof of this result. So, now I have to stop today's class into this problem. And now, in the next class, we continue also about the 1-1 and onto mapping and some special type of a linear transformation we have to define with the help of this 1-1 and onto linear transformation. So, thank you for this lecture. Continue next class with the inverse of a linear transformation.